Hello everyone, this is Dr. Webb and welcome to this calculus video. So in this video, we're going to get an introduction into what are called related rates problems. So why don't we just jump in right into an example. And so this equation here is an example of what's called a Cobbs-Douglas production function. So Cobbs and Douglas, one was a mathematician and one was an economist, and they were working in the first half of the 20th century, and they found, looking at a bunch of data of countries, that they could model the country's production, their GDP, well if they knew what the labor and the capital was, and it was modeled by this type of equation, which is now called a Cobbs-Douglas equation or Cobbs-Douglas production function. And so in this one in particular, we have P is equal to 2 times L raised to the 3/4 power times K raised to the 1/4 power. And so for a Cobbs-Douglas production function, it's important that these two exponents on L and K add up to 1. And so here we have 3/4 and 1/4. And in this equation, P represents production, generally thought of as gross domestic product for a country, although this sometimes is also used to talk about production of companies. The L here represents labor, and the K represents capital. And so capital here is thinking about all the other physical things other than labor that you need to produce goods, like natural resources, buildings, factories, materials, all of that. Okay, so here's the equation again. Now suppose this is our equation modeling production, and we know that L is 11, so labor is $11 trillion, and capital is $8 trillion. Then can we figure out the production P? And the answer is yes. We simply plug them in, put them into a calculator, and out spits 20.3. So we'd say that the total production of the country was $20.3 trillion. Well, so we can figure out P. What if we were also given the rates at which L and K were changing? Could we then figure out the rate that P is changing as well? Okay, so we're thinking about L, K, and P. These are all quantities that are changing with respect to time. That means that really we can think about these as actually being functions of time. If they are changing with respect to time, they are functions of time. So we can rewrite our equation before. So here it was before, but now rather than thinking about P, L, and K as constants, we're actually going to think about them as being functions themselves. And so now we're thinking about this as an equation that is actually equating functions together. Okay. So suppose we have that currently there are $11 trillion spent as labor, the same as we had before, but now we know that the amount being spent on labor is actually decreasing at a rate of $1.2 trillion per year. Okay. So the $11 trillion spent on labor, that means that right now L of T is 11. And the decreasing at a rate of $1 trillion a year, well, so that's talking about the rate of change of labor, and so that is the derivative of labor. And it's going to equal minus 1.2. The minus sign is because it is decreasing. Now suppose that we have that capital still is $8 trillion is being spent on it, but it is decreasing at a rate of $500 billion per year. So currently, capital K of T is at $8 trillion, and then it is decreasing at a rate of $500 billion a year. So again, that's going to be talking about the derivative of capital, and that's going to be minus 1/2 because it's decreasing. So K prime of T is equal to minus 1/2. So we want to know about how production is changing. And so to get p prime here, we're just going to take the derivative of the whole equation. Now the left side of this is just p by itself, and so when we take the derivative of that, we're going to get p prime, which is what we want. On the right-hand side, we have this product of these functions to powers, and so this is going to take a little bit of work to figure out what the derivative on the right-hand side is. Okay, so we're going to take the derivative in terms of t, in terms of time, of 2 times L of t to the 0.75 times k of t to the 0.25. So the 2 is just a constant, so we can pull that through. And then we've got L to the 0.75 times k to the 0.25. So this is going to be, we're going to need to use the product rule. And so one function, f, is going to be the L of t to the 0.75, and our other function g is going to be k of t to the 0.25. And then when we take the derivatives of both of these, got to remember that we really have a chain rule here because L of t is a function itself. And so we're going to use a chain rule where our outside function is going to be t to the 0.75, and our inside function is just L of t, and so then derivative of the outside, that's the power rule, 0.75t, and then subtract 1 is going to give me minus 0.25, and the derivative of the inside is L prime of t, and so plugging this into the chain rule, derivative of the outside with the inside plugged in, L of t to the minus 0.25, and then multiplied by the derivative of the inside, which is L prime of t. And then same thing for g prime. So we got to use the chain rule again, but now our outside function is t to the 0.25, and our inside function is k of t. Derivative of the outside is 0.25t to the minus 0.75 after we subtract 1, and the derivative of the inside is k prime of t. And so plugging this in, derivative of the outside with the inside plugged in, and then times the derivative of the inside. Okay, so now we have everything we need for the product rule, and so we can finish this off. Let's change the color here. So we need to do, product rule is f prime g plus f g prime. So f prime g is going to be 0.75 L of t to the minus 0.25 L prime of t times k to the 0.25, and then plus f g prime L of t to the 0.75 times g prime, which is going to give us a 0.25, which I'll pull out front, k of t to the minus 0.75 times k prime of t. And that looks a little bit nasty, so let's clean this up. Oh, nice and clean, and there it is. And then we notice that we have L to the minus 0.25 and k to the positive 0.25. And then here we have L to the positive 0.75 and k to the minus 0.75. So we actually can combine these terms together to compress this a little. And there we have them simplified a little bit. And so everything here is in terms of L, K, L prime, and K prime, and we know all of those values. So this is what we have, and we know these values for L, K, L prime, and K prime. And so to get P prime, we just have to plug these values in. And so we plug them in, we get P prime is equal to 1.5 times 8 over 11 to the 0.25 times minus 1.2. plus 0.5 times 11 over 8 to the 3/4 times minus 0.5. Plug this all into a calculator, and out spits minus 1.98. And so this is, again, this is talking about the change in production. And so the minus sign says that production is currently decreasing at a rate of $1.98 trillion per year. And that's just what I said. So production is decreasing at a rate of $1.98 trillion per year. Okay, so this type of problem, this is what's called a related rates problem. Okay, and so when we have a related rates problem, really what we have is we have an equation between different quantities that are changing in terms of time. And we know information about some of them, and we want to find out new information about some of the other quantities. Okay. So the strategy in general to do a related rates problem is first you need a formula that relates the quantities together. So in this case, this was given to us. P is equal to 2 times L to the 0.75 times K to the 0.25. Other times you might need to use some trigonometry or some other information to figure out what this formula should be. But you always need to start off with an equation that incorporates all of the quantities. Then we're going to take the derivative of the total formula, and we're going to treat everything that's changing in terms of time as a function of time. So we're going to treat everything that's changing as a function of t. And so this was the next big step we did. Wherever we have functions that are changing in terms of time, we are keeping its derivatives because those are important in this. And then we plug in the quantities and rates that were given and then solve for what we want. So in this case, this was already essentially all arranged nicely for us. We just needed to find p prime of t. So that is all for this video. We will definitely do a lot of examples of this together. And that is it. So I will see you again soon.